Okay, as I said to the other guys already, I have prepared something just to explain you a bit of Fuse, like one side. Yeah, so this will be maybe something like 40 minutes or so, maybe a bit faster, maybe longer, let's see. So it's more like a technical aspect of Fuse on how to do things there. And after that, we could come to a Q&A and you could ask like more specific questions, or Nathan might also show some particle stuff or whatever. Yeah, so that might be a bit more loose then. Okay, so then let's start by sharing the screen. Okay. Okay, so I guess you see now my patch here and the output. So I thought today we cover the topic of how can you like extend Fuse? You know, there are already a lot of nodes, but what are ways to write your own nodes? And I have prepared already this little patch here, which shows like 3 different ways to implement a remap function. Yeah. And we will cover 3 ways. First way is to patch it. Yeah. And then one way is to include another shader where this function is already applied. And the third way would be to use kind of the Fuse template syntax to write your own little code snippet, right, for this function. And we will also see a bit on how the source code that is generated compares, yeah, and try to get some deeper understanding on the Fuse pipeline. And okay, so let's get started. So here we directly see the output of this function. So it's a remap where we have a value input and a source min-max and a destination min-max. And like as we change those values here, the output of the remap function gets different. So I will not so much explain the rest of the patch. That is where we pick up from the last session. Yeah. So if there are questions, you can look over there where I got in more detail on those things. So let's see how we put the remap. Yeah, this is basically the patched version we will get to. I will now delete it all and we will basically patch it from scratch. So how can we do that? Say we have all our in and output pins already. And basically the remap function is explained by you have a source minimum and source maximum, and this is used to normalize the input, and then it is scaled to the destination minimum and destination maximum. And so to achieve that, we will now include some math. And for this, we will use these Fuse math operators, right? So the first thing we do is we take our input and we subtract the source minimum, right? First part of the rescaling. One thing you notice now is that these things here are generic. So you see this is, I hope you can read this. This is, scale that up a bit maybe. This is a GPU value of T5. Yeah, so there's no specific type now. We could type it. So we could say configure, and then here we could say GPU value, and then put in float. Right? And now this would be typed. So now it would only work for GPU floats, meaning like float variables, right, on the shader. But as we also want to work this remap function work for vector 2, vector 3, yeah, we take this one out and leave it generic. So, and we see, because this operator, this process node here already brings like the type of GPU value, because most of the operators in Fuse are generic. we already also get a generic function when we work with them, which is quite nice. So you kind of only patch this node once, and then it's working for float, vector 2, vector 3, and vector 4. Okay. So now we have this minus there. And now the next thing is we need to divide. And we divide by the range. So this is source max minus source min, then like this. Okay, so now here we have the normed value, and now we need to bring it into that range described by destination min max. And we do that by first multiplying with the range. So again, the minus, and we take destination max minus destination min, connect this here, and then in the end add the destination min. Okay. And this should now be our remap function. So let's see if it is working. First I will remap and rename it. So here we have it, and you see it's not typed yet, right? So because it's generic, but you also see that the input and output types match. Yeah. So once one of the pins is connected, also the other ones get clear. And I already prepared some pads here, where I have all my inputs so that the patch doesn't look so cluttered. And like here in text X, we have the text chord coming from Fuse, which is a semantic. And then with this X thing, we get the text chord X. Right. So if you look here in our preview, you see we have this texture coordinate. Right. And if we just take the X value, you see this is a input gradient that we have. And now we connect this one to a remap function. And we now put it out. So, and what you see now is that this stays black, which is probably not what we want, because we want to set some default values, right? So that our remap function is working anyway, if we connect something or not to the min-max values, that it's outputting something nice. Okay. And so basically what you see now in the shader code, so this is the part that is now generated from this patch. And like here you see a lot of zeros in there. And this is because there's stuff not connected. And if stuff is not connected, a default value is chosen by the system. And this is usually 0. And this is really just meant to make sure that the shader is compiling, and you don't get null pointer exceptions. So it's really basically just so that your patch is executing. But we ourselves know what are maybe more useful values. So we want to maybe come up with our own default values. And there's a node for this. And this is called check default. And there are different versions of this one, right, of the check default value. So you could, for example, we come to the other ones later. I don't want to get too deep now. This is always like something I have to be careful with. Like I could really get like probably too deep into stuff, but we will take this check default thing and this node. So if we connect this one here and this one there, it's now checking if something is connected to this input, right? And if it is not connected, it outputs a default value. And in here, we will now say what is the default value. And for this max thing, we want to set it to 1, right? And this now means if nothing is connected to destination max, it is set to 1. We will also do this for the source mux. So here it will be the same. And we can also do it to the min values, because then people know what's going on when they look into the patch. Do that here. Should be 0. It should be 0 as well. Okay, so now we have put this default check on every input. Now if we go back here, those values are set. This is currently not evaluated because it is in a cache region, so it is still black, right? So now when I restart and everything worked right, so now you see it's working, right? Because we take an input value from 0 to 1, yeah, and also have like the source and destination range from 0 to 1. So actually this remapping is not doing anything currently, yeah. But if we look now into the shader code, you see that those values are like now 0 and 1, yeah, and not all 0 anymore. And now when we connect our variables here, we can start playing with those. Yeah. Now they get also controlled. Yeah, so you see our patch working. Yeah, and this quite often gets you quite far, right, with patching stuff. So you can simplify it stuff. The cool thing, it's generic, yeah, so it's working for most of the types. And like just to cover it quickly, this operator is from the Fuse math package. And if you look in here, oh, there's something red. I need to check this later. But there are a lot of, so we have all the operators like plus, minus, and a spectral version. That's something I also show. And then there are all standard HLSL functions, right? Like sinus, dot, cross, and whatever. Yeah, and some more functions, some constants. So it's all pretty much there. Yeah, and then one last thing regarding the operators. So if I edit here, so they are all pin groupable. Yeah, so you can add as many inputs as you need. Okay. Any questions so far? Okay. I hope this all makes sense. So then I would come to the next way to implement functions in Fuse, which is to implement a custom function. Okay, so I take this all out. So this will look a bit different, right? So in Fuse, we have a custom function node. It's called custom function, right? And this node also outputs a GPU value. And it allows you, what you see here, to define a function with a code template. Yeah. And this is basically a function that you can write yourself, right here in an IO box in VL to execute something. So let us put this here. We will see how this is going. So, and the other thing, this node expects is the function name. So this is remap. We can also pass over a default value, and then we will also include all our parameters for the function. And this is also a pin group. So we have this 5 parameters. So we need 5 inputs here. So this is what we do. We connect them. And now the way this works is we basically write our remap function here as shader code, right? So if I do this for the type float, we would write it as remap. A bit. Hope you can read it all. Okay, so we start with the parameters. So this will be like before. So we have our min and max values. Right, and then basically we fill out the same formula that we before just patched. So we take our input and we subtract source min, and we divide this by source max. So this again gives us the normalized value. And now we will multiply this with the range, with the destination range. And in the end, so this is our function. And it's basically the same math that we had also in the patch before, right? But what we see here, this is now typed, but we still want to have a generic patch, right? So, and this is the question, like, how can we get this shader function generic? Yeah. And here comes some kind of template syntax that we have in Fuse. And we have some templates which are already given by Fuse, and they are written like this. So you have this parentheses, and then you have the template name. And in this case, it's result type. And this is something that Fuse knows because it can look up the type that is connected to the custom function. And then it can see like, okay, like dependent on where you connect it, this might be a vector2 or a vector3 or a float. So this is resolved at runtime while you are patching, right? And then this result type will now be replaced by float2, float3, or float, dependent on what you connect. Yeah. And so now we will replace all our floats because all these types need to change according to the type that we connect. So we replace all the floats with result type. Okay. And then we have one more to change because we might have different versions of this function. Fuse needs to add some kind of hash code, whatever, yeah, to the function. And to know where the function name is, we need to take out the function name in here and replace it with another template value, which is called signature, right? And the signature is representing this function name here. Yeah. So let's see if I got everything right here. I mean, basically, this is now a simple case for this function, yeah. But there is functionality which we can currently not build with Fuse, for example, for loops or something like this. And there you could not patch it and to still allow you to build like your own kind of nodes where you could have a for loop or other stuff. We have this custom function mechanism. Yeah. So let's see if we replace it into yeah, so in this case, this is now taking the type of the custom function, right? Because the custom function does not know what kind of stuff we connect to it. It could also be a texture, for example, right? And it could be different types here, right? So for example, if you have the dot product, we would connect two vectors and get a float out. Yeah. So we need to do some typing here. So to say, we know that all of these input values, we don't know the type, but we know that they all have the same type. Yeah. And we can do this by adding a type to this function, to this node signature here. And now we can configure those nodes and say you have the type GPU value T. Now we do this for all the nodes. Because once we have connected one node, all the other one needs to have the same type. Okay, so now it's typed, it can be resolved. And now when we go back here, hopefully it works now. Let's see. Connect them all. So output there. Okay, so here we have the output. So we will switch now one to this node. Oh, it's not compiling. Yeah, so I guess something is wrong with the template syntax. So just to avoid that, I have already prepared this node, which we still not working. Let's see. It was just working. That's pretty much the same. Yeah, so now it's working. So something was wrong with the node, but nevertheless, as you see here, it's pretty much the same thing. Might have messed up something with the signature here, right? But you see, it's pretty much what I have just written. And I have also added like the check defaults here from the node before, right? And yeah, this is now another way to encapsulate functions or new function that we do not provide into a custom node inside Fuse. And one other thing to take away is this kind of typing here, yeah, and to understand a bit, yeah, like how yourself need to type the system, because this, to a certain degree, it can be inferred by Fuse, but on another level, you need to explain the typing of the functions. Yeah, so I guess this might be a bit more complex than just patching. So if there are any questions according to this. Okay. And now if we look in the shader, maybe just to see how it compares. So if we look again to our patched version, so basically everything that is patched is directly put in and executed here in the shader file directly. So this is not really smart, this is more dumb, but still the shader is fast, it compiles, yeah. So you see that the remap function is just directly put in here as with all the calculations without introducing a function, which is something that might change in future versions of Fuse, but currently is the way how it's done. And with this custom function, you now see here is our evaluated function from the template. Marco, I take you. So here you see the signature has changed, and for the result type, we have the float value written. So this is something that Fuse then does. And if we would now have a different input, like vector 2, let's see. So if we would connect now the text code, I will not do this now, but it would then change the signature here. Yeah, Marco.
Can you show the inside of the plus node inside of Fuse Core Math? I think it was.
Yeah.
Because I'm still trying to understand what's different to a regular plus in Gamma.
In Gamma, okay, I see. Yeah. Okay, little sidekick here from the functions, explaining a bit like the operators and functions and how this is how this relates to Gamma. Mm-hmm. So if we look here in our patch node, we have various operators. Now, if we look into one operator, in this case the minus, you see the first thing is because we have this pin group. Yeah, we also have another version of the minus, which just gets a spread of values of GPU values.
Is fine.
Yeah,
it probably doesn't really.
And now if we go into here, yeah, we actually see this is a typed operator. And what is this? This is now then connected to the untyped operator, right? Because a typed operator is, for example, like a plus and a minus, right? Which is of a type, for example, float, and you have like two values which you add, and then the value that gets out has the same value. It's the same type. So if you add two floats, you get a float. So this is like typed because the in and outs have the same type. But for example, for a comparator operator, right, you might have two integers, but you get a Boolean out. Yeah. And this is like when you have another, it is untyped, yeah, because the types do not match. Yeah. And if we look in here, this is now getting more deeper into Fuse, right? So here you see we want to create an operator node. Yeah. And this is maybe not something you need to really remember, but just to understand maybe on what level it gets really deeper into Fuse, right?
I see.
And this operator node, this is now something that is written in C#. Yeah, so we have parts of Fuse which are not only in Gamma, but we also have parts which have a counterpart in C#.
Yeah, you basically wrote and patched some primitives, and the plus is like the primitive you.
Exactly. But this is pretty much the primitive type, and I will not really, I will pretty much spare you open C# code, but just for
Yeah,
you.
you don't need to. You don't need to. I wondered, why is it not possible to patch something on
Yeah.
CPU?
Yeah.
Just copy paste that to GPU. You know, you have to like.
Yeah, it's different because it needs to do different things, and just
Now,
I will get in more detail.
I understand now.
Yeah, yeah. And so basically, this is what you see here. This is the code behind, and just to highlight this, this is now the same shader syntax which I just had in this custom template node, right? And this is really not, you do not need to fully understand it. Just get a feel of what are the mechanics behind. Yeah, and yeah.
I think that answers my question. Thank you.
Yeah. Okay. And so something that is really different also with Fuse is, in the end, the graph is not executed like the Gamma patch. Yeah, it is describing the shader, right? So in the end, behind every of those nodes is pretty much a string, which is just filled out, and in the end, all those strings are evaluated to the finished shader. Yeah. So every node represents a small little shader function. Like if we take the Zine function, right, it will put together the string for the Zine, yeah, for the Zine function in HLSL, and this is what it does. And by putting together the strings, it's kind of mimicking the VL visual graphic language, right? But this also means that sometimes the behavior is different because behind this GPU value is pretty much a string, yeah. And what you do is you put strings together, right? It still is an object graph, yeah. But behind this object graph, this is a string representation for the shader. Okay, and this maybe also kind of explains this kind of custom function, right? This is the approach to, like with this operator node, yeah, where the syntax is kind of hard-coded and already comes with a node, yeah, gives you the possibility to kind of inject your own shader code, yeah, and this more on patching level without the need to write C#. Okay. Yeah, I hope it's not too dry, but this is also some kind of reference material, you know, which we put on YouTube so that once you get more into the details, you can look it up. And I think the handy way for today is you kind of heard from it. And if you know you need a function, you know about the 3 different ways, and you might look it up again on YouTube or look into this patch, which is also in the help patches to get an understanding. Yeah, and I think we're almost there, so let me just quickly look into the last way, because one thing you have a lot is like big shader libraries, right? Where other people already wrote shaders and have a lot of whatever handy functions, and you want to make it possible to use these functions directly in Fuse and in Stride without thinking too much of it. Yeah. And for this, we have the mix-in function node. So if I go in here, and the mix-in function node allows you to include a shader file and then call this function. Yeah. So what the mix-in function node expects is, like with the custom function, it has a pin group, and it has all these arguments which come in. So again, these 5 arguments. You see again, like with the custom node, we also have declared the type here. Yeah. of t. And then we also have configured all of our inputs to GPU value t, right? So it's the same thing like with the custom node. Yeah. We also give it a function name here. Yeah. And we give it a mixin name. And the mixin, this is a shader that the L needs to find in your folder. So let us now look, where's this shader? So this is a place where we have our patch, so explanation, implement the functions. And here we have this shaders folder. And this is where we need to place our shaders that can be then referenced by the system. And if we look in here, here we have this remap mixin2 thing. And let me open this. So here we have this shader. Sorry. Right. So this is our remap mixin2 shader. And of course, this could be like a far bigger shader with a lot of more functions or whatever. Yeah. And we can call all of those functions inside our patch, yeah, by providing this shader file and then the name of the function that we want to call. And because in this case, what you see here, we have one version of remap, yeah, for every type. So for float, float2, float3, and float4, because unfortunately we in the HLSL shader do not have a generic type so that we could just write it once, like with the custom template. You now need to make 4 versions, right? But there might be also other shader files which give you like color operations or mask operations or whatever you need. Yeah. And then this is a mechanism to get this into Fuse. And now if we compare again, so now I will switch to this third option here. And now when we look here, you see that we have here in our mixins this remap mixin2. Yeah, so this is the shader include where we include this shader file. And then here we have the call of the remap function. Yeah. So this happens here. And this is where we call the remap function, which is declared in this remap mixin file, which I have just shown. Okay. And we also use this mechanism quite a lot inside Fuse. So we also wanted to make this available to you. So for example, if we look into our library folder here and look into shaders, so there are a lot of shaders and they are included into Fuse. For example, the noise calculations or some math. Yeah, so something that we could look is like, for example, Fuse core transform, right? And here you see there are a lot of transformation functions which create matrices, and you can make a lookup matrix or a rotation. So a lot of stuff that you would not like to patch, but you're just happy that it's there and you want to be able to patch with it. Yeah. And so we throw it all into these kind of header files. And if we now go back to our math package, so here we also have our transform category. And in here you see a lot of process nodes. For example, here the rotation. And basically what you see is here, we just have a mixin function where we input a vector and then apply some rotation. Yeah, and what we actually call is a function from the mixin. Yeah, so this was pretty much the explanatory part of this workshop. Let me know if you have more questions. Otherwise, you are hopefully set up now to get your own shader functions and whatever you need into Fuse, into Extended.
Yeah, hello.
Hey.
Christian.
Hello.
I have a little question, because I understand about all the creation of the functions, all this, but what about when you want to move, for example, from an array from CPU wall, and you want to include it in this kind of functions? For example, you make a remap, but I want to remap 1,000 values from CPU and pass it to a GPU value.
Yeah.
What is the flow about that, and if it's possible? Because I was digging about it, and it's the only part that I still not have clear. It's with buffers. How to deal with that?
Yes. Okay. Yeah. We can come to that.
Okay.
Perfect. Yeah. I can show you that, how this relates into our compute system. Yeah.
Yeah. Just in the basic thing, like how to convert this array to a buffer, and this buffer read it in GPU, so we can upload all this data from CPU to GPU to make other things. It's something really nice. I think we can know.
Yes, I understand. Let me see if I can shake it out like quickly without too many bugs. Yeah, because it's not. Yeah, I have not really prepared, but I think I can sketch it out. Yeah, and then maybe this will also be something that we will cover in a later workshop in more detail. Yeah, but just to give you an idea of how it works. See, I think I have hopefully a shader function, which is already quite close to this. Yeah. Okay, so this looks now a bit more complicated. We also have a system to simplify it a bit. Yeah, but if you just really want to work with buffers, then this is pretty much the way to go. Yeah. So like in this case here, we have a buffer. Yeah, and this buffer gets created. This is pretty much, just covering a stride buffer. So you can also get data from a sequence or whatever, from another collection. And so here you see, here's where we calculate with this buffer. Yeah. So here we have the buffer which gets in, and we have the index. Yeah, and the index also is this dispatch thread ID. So basically now we are on a compute shader, right? And maybe to make it a bit more readable, it would be like, instead of the index. So this is from the dispatch thread ID, the X, which we connect here. And here we have our buffer. And we get the buffer value. And here now we just add a constant value, right? Which is 14. But in here, we could also have multiple other buffers and then apply the remap function here. Yeah, so what you see here is we have the same buffer again, and here we set it. But you could also have, of course, multiple buffers. And instead of taking the same buffer, right, and replace its value, you can have another buffer and then insert the value there. Yeah. And I think Nathan will also show, or maybe I get into it just briefly. So like we also have this kind of map function, of course, already in Fuse. Yeah. Which I just showed in the example.
We can show the example with the particles, right? How to use the buffer. But I can show it.
Yeah. And now here you can use the same map function, right? To then fill your buffers and whatever, and read them back or use them somewhere else. But this is stuff we will cover in more detail in a later workshop. Yeah, I hope this answers your question for now. Is that okay?
Yeah, yes, for sure. Yes, it was a little quick view about it, how to deal with that. But it's amazing because you can use any custom function that you do and feed it with custom data, and it's very nice. It's super.
Exactly. So we really like covering now the low level of use, but it really applies to many other topics as well. You know, also to work with SDFs, to work with buffers, to work with simulation. Yeah. So I think this is for this reason, it's good to have an understanding of the possibilities on this low level. Yeah, because get your own kind of functionality from other resources which you might already have, you know, from other shaders that you have already written in projects, you know, and you want to get this into Fuse, you want to make this patchable, then this is the way how you can do that. Yeah.
Yeah, super cool, man.
So I can eventually show this little example with the particles, because in the end, it's really simple. Can you allow me to share the screen?
Yep. Okay. So hope you can share the screen, Nathan.
Yes. Do you see anything?
Yep.
Okay, this is what right now during the code, I'm still going through the help patches, cleaning, fixing. And this is one of them. As you see, this is a very basic particle system. As we are familiar with now, we have some forces, integration, we set some data, compute stage here, compute system, and then we draw this particle. We emit them. And as you see, the particular thing about this patch is that we want to provide a set of points where to emit from, and also a set of colors. And this is basically a way to do it. Usually, if you want to pass data to the GPU, you might use buffers, or it's the way to conveniently provide data to the GPU. And here, it's exactly what we're doing. We are using, we are feeding some random spread into buffers, and then, yeah, basically, so that's the buffer, the Fuse buffer, and then we use this buffer to input this buffer into the shader, and then using this function, you see this part. I should already lay out a bit different to make you understand that this part here is somehow like being inside the compute shader, inside the compute shader of the particle of the emission. It's where you can get you can read from the buffer. So this is like the input pin of the shader, and this is where you read an instance. And we use, I don't know if you're familiar with compute shadering, but usually you basically have as an input of your compute shader, you have the dispatch thread ID of your thread. So you have the ID. So you can use that, for example, to read each thread reads one slice of the buffer. And this is what we are doing here. We are using the thread of the particles to read from the buffer. Obviously, wrapping the indices with this element count so that they don't get outside the buffer, but if the ID of the particle is bigger than 10, then you will start again and pick the first of these points and second. So you will wrap these indices into these 10 elements. So what you get is a position, because this is a buffer containing some random position. If we can change the seed, you will see that there will be other position there. And we feed these into the position of our emission. So this is a simple way, and the same is for the colors. No? Let's distinguish again. So now here we feed, this part is CPU part, and it's basically what would be outside your shader, no? A normal shader. Usually we're used to have these shader nodes with our patch and then some inputs, the shaders. So this is something that you would still patch, in Gamma, okay? Then you input these buffers, and then within the Fuse world, in this case, within the compute system world, where we patch compute shaders, this is the way you read these resources. You read these buffers, and you can do whatever with it, whatever you want. In this case, we are using to set the initial position and color. But in general, yeah, this is the way you can easily read resources, and this works for buffers, but we also have like a sample texture 2D, for example. So where somehow it works the same. Somehow you can recognize some patterns from the shading language. Obviously, you have some resources, and then you have some intrinsic functions to read these resources. And we can read buffers, we can read the textures, and that's, for example, how some modules of the particles are implemented like that. The texture force field, for example. Internally, just implement this sample texture, so you can sample a texture and use the data from the texture to as a force for the particles. But if you open that module, you will see that. Actually, I can show you. I think. I know it's already open. Touch. There was texture. Yeah, this module now, texture 2D force field, which is literally reading a texture in this case that we provide. Instead of a buffer, we provide a texture. Internally, we use a sample texture node to read some data. We are interested in just X, Y, Z. In case we can normalize it, but then these get used as a force into the particle system. So yeah, it's quite simple at the top level, no? It's quite intuitive the way you handle these resources. That's it. Questions? Everyone is happy.
Yeah, so we have some questions in the chat, which I just got aware of. So we might jump back a bit to the other patch, which I made before, and then answer those questions. Yeah, we will definitely cover also the particle system in more detail with future sessions to explain that, because it's not only particle system, it's basically really compute shader, and you can also just make calculation there of any kind, buffer related, and write out the buffers and whatever you need to do.
So let's go through the questions.
Yeah, let's go through the questions, exactly. Okay, so I want to go back here. Let me see, where's the chat? There, okay. Yeah, so one question was, are different input types possible? And another question from Randall, can I do T1, T-type, which is type related? So let me answer both. Yes, you can do that. So if we go here into the remap function, which I will now just disconnect here. So now we had all of them had the same type, but of course we might have a function, for example, where or maybe I just start better, sorry, with just an empty function, because in the end it really doesn't matter. We talk about the typing. Okay, so this mixin function, as you see, receives arguments, and this is a spread, and this is of the type abstract GPU value. And this is like kind of the super type of all GPU values. So textures are abstract GPU values, GPU buffers in Fuse World are abstract GPU values. Anything is an abstract GPU value, right? And this means like a function could receive any value. It could receive a texture, it could receive a float, a vector 3, or combinations of those. So you need to be able to type this. And so how we do this is, like in here, I now get like 3 arguments, right? And even the output could then be, of course, like again another type, right? Yeah, so let's put in one more parameter to explain it all. Okay, so let's say, so what you see now, these values just infer their parameter, their type from the function, which is abstract GPU value. But this is not really helping us. So we want to say what is really like the type that you receive. And yes, we can put in more types here. So we could, for example, say Tin and Tout. Like this. And now in here we could say, okay, this is our output type. So this is GPU value of the type Tout. What's going on? Needs to be generic. Yeah. So I also need to make this one generic to make it work, the process node. And we can configure this one here as well. And this is now GPU value Tin. Right. And also the second argument might be GPU value Tin. And then here you might just have a multiplier for the output, right? And so because of this, this would be also of the type Tout. Yeah, and here, for example, we could say we know that this will always be a float value. And then here we could directly type it to GPU value float. Yeah, and then we have our function explained. So we can have multiple types here, can be even more than 2. Yeah, and this is pretty much just C# feature, yeah, which is like behind VL, which you are using here. Yeah, and then you can apply those types in here and describe what can be connected. And once you connect some parameter here at Tout, then this type is also defined. Yeah, so if you connect a GPU value vector 3 here, then this will also be of type GPU value vector 3. And the same here. Yeah, if this Tin is GPU value vector 2, then this is also vector 2, whatever. Yeah. So like with this typing here, you get really flexible. This is again what we try with Fuse. We do not want to have like a lot of type nodes, yeah, for all the combinations. What we want to keep them adaptive and generic, so that we only need to provide one node, yeah, and then this is working for most of the cases. Yeah, and that it's easy for you to change dimensions also, because for a noise, for example, this is often what you do. You start with a vector 2, and then you want to have it animated. So you add like the time, then you have a vector 3. And in our case, you do not need to repatch it, because you just have to insert the vector 3, and then all the other stuff will be inferred. Which is of course not always that simple, yeah, but it reduces the amount of repatching you need to do to apply those changes. Yeah, the order of the the order of the pins exactly. So yes, the order of the pins matters. This is exactly like how they are connected. So if we go here into our remap custom function, for example, so you see like the order that we have here, value, source, min, actually these names don't matter at all. It could be anything. This is not the mapping. Yeah, the mapping is really just by order. And so we have our 5 arguments here, and they are ordered as they are inserted here. So the first argument here is the first argument in our function, and the second argument is the second argument in the function. Yeah, Randall asks, how about reading the values back from GPU to CPU land? Yeah, so this was, let me see. Where was that example? I still need to open it again.
There is a readback.
Exactly. This is a readback thing. So this is what you see here already. Here the small, right? But we have our buffer, and then here we have this native buffer type, and this can be inserted into the stride node here. See, so this buffer is still a stride thing, right? And even if we change it in our shaders, like in our Fuse shader world, this is a GPU value buffer, right? But it's still connected to this kind of instance that is here in Stride. And whatever we do in Fuse is basically really just a shader. The data is still here. Yeah, and this is where you access it. And here in this readback float, yeah, you just get it and then you have it back in CPU world. Hope this answers this question. Okay. One more. Okay, yeah. You're welcome, Randall. Yeah, I hope next time I will try to keep the chat in mind. So not make it like such a delay, but gladly I realized there are a couple of more questions. Yeah, and there's one more comment from Tevian. Use readback buffer for non-blocking version. But again, all these buffer topics we will definitely cover in a later workshop in more detail. Yeah, direct readback is always never what you want except for debug. Yeah, so this is like here's a debugging case. So let's see, readback buffer. And Stride. If we connect it here. Yeah. So here we would connect now the output directly to a mutable array. Yeah, and then you directly have the data at hand to work with it. Okay, even if it's more than just like this 67 here for debugging. Okay. So, I mean, this workshop is also for asking questions or making suggestions to Fuse. So if you have anything on your list, you know, like feedback-wise, what you like, what you don't like, or stuff that you see worth discussing, let us know. Now is the chance. We could also look into questions like regarding what we could explain next week in the workshop. You know, so if you have any topics that you would like to be addressed, then let us know as well.
I was thinking that, what about showing some of the help patches that we are building for feedbacks?
Yeah, sure.
I wanted Service Cody to do that, but okay.
Yeah, maybe you do it then, Nathan.
Yeah. Just for feedbacks, because we are discussing if they are fine, if they are, we are building them. So let me share again. What is a sign distance field? Now, as you see, it took a bit to load the previews because basically instantiating one of the tooltips, one of the renderers per object. So this is one of the things that we are discussing now. Here was fine, but then there's another patch in which there are 40 of this. It takes, I don't know, like 10, 15 seconds to load. But in general, this is the approach. We want to enrich the patches as much as possible with visualizers, right? So that you really see what we are talking about. And you can always play with them. You know, this is crazy cool to be able to directly have feedback with some explanations. You can go down and see, okay, this is the 2D, the 3D version, the concepts are the same. So really trying to be didactic in this sense with some links for external resources. Trying to come up. This is the killer patch. This is an overview of all the sign distance fields. I mean, these tooltips are amazing. It's like an art piece. That patch just takes a few seconds to load. And when it's loaded, I think it's really beautiful because you see each one of them properly. You can still play with them. So you see the 2D ones, and then you go there and you see the 3D ones. It's just nice. So as you see, we're trying to keep an aesthetic sort of thing. Very simple patches, our patches clear as much as possible. Descriptions. So yeah, what do you think about it? Do you like?
I think it's really beautiful. You know, it's super intuitive for an artist, as you say. It's very, very beautiful. Because you see directly the thing and the result of the node without.
Yeah. I think that the tooltips really makes the difference, honestly.
Yeah, and these tooltips, these new tooltips are super beautiful. You know, like no any more info, just the.
Yeah, I hardly asked for that. It's super minimalistic. But still, you can add all the details. If you hover with your mouse, you still have the old tooltip, no? But then when you pin it into the patch, you're interested in the value, no?
Yeah.
Okay. Yeah, that's why for sure we want to make heavy use of tooltips because they are very explanatory.
Yeah, so we have some looking great, and thanks for raising the bar in the chat. Yeah, of course, be aware every tooltip is its own shader, and therefore it takes a while. Yeah, so in this educational stuff, it makes sense to have a lot of them, but of course in your applications.
The good thing is that, I mean, if you get out of the patch of the tab, you don't compute anymore those tooltips. That's why when you go back to the tab, they get re-evaluated, re-instantiated. So it's a dynamic instantiation of these viewers. So it's just when you are working in the patch that they get computed, obviously. They need to render something. Then when you are outside, outside your project, and you don't see them, they don't consume. So that's good.
Yeah, and this is also like regarding how you structure like your fuse patch, you know, as you can put your parts into different process nodes and then put it all together to a bigger graph. You can have like an overview, but still not too much performance. Yeah, so that you can patch on this specific part, have your 5 tooltips, and then you can switch between them.
Come on, guys. Watch this patch. It's an art piece. Congratulations to Silvescu and,
Yeah, it's
and
awesome.
Kyle. They are doing, look this. These two, and here it explains all the way to combine the union, intersect difference, and all the other possibilities. It's just, I mean, it's a thesis, no? It's a PhD. It's crazy. It's super beautiful. I hope you like it. I think, again, it's the same thing for the 3D part. And the cool thing is that you can always still play with these. Oh, it's just amazing. Bravi. Yeah. Cool. That's it. My plan was to finish today to fix some stuff and push a new nugget today so that you can check the latest state with the latest help patches and give feedbacks and report bugs, because we are really pushing these days we are getting close to something. Then just since we are here and saying, since we are in a rush with the development and there are so many things to do, we still need to find a logo for Fuse. So I kindly ask all the designers here to give us some suggestions, because we don't have much time to just think of that part. So please just come up with ideas, visual ideas or sketches, and and help us. I know you're
just take one of the tooltips, Tebian says.
Maybe we should patch it, actually, the logo. Why not?
Yeah. So Silvescu will be the main for the logo.
Yeah. That's it. And then, again, we are collecting materials, like a screenshot of experiments that you do, and because we would like to have some material to promote the project. So feel free to post. We already wrote this into the chat, but I encourage you to do it so that we collect more stuff.
All right.
Well, then.
Yeah, could maybe relate to the Stride logo, Tebian just said. So I know there were a lot of versions of the Stride logo already. I don't know if we could also relate to those other versions. Let's see.
Yeah, write all these ideas in the chat so they don't get lost. So that we can collect them. And what else? I don't know, did you ask about the next session? Would be nice for them to see. What would you like to see in the next session? Which will be next Wednesday, I don't know, just after the meetup.
Yeah, so maybe we do some particle stuff next time, or some more high-level stuff, because like the last ones were a bit more detailed.
Yeah, we can do, well, we can have a look at the compute system from the higher perspective of the particles.
Yeah.
And let's see, I mean, we'll show something at the meetup anyway. And so, and I don't know, maybe because we will be in a rush. So I don't know. Let's see if we can manage to do the next session the next Wednesday. Could be that we skip it.
Yeah.
But
we will let you know in advance.
Not because we are lazy. Trust us.
Yeah. And if there's any other input, just drop it in the VL Fuse element channel. Yeah. And then we can still react. So if there's anything that you would like to get us prepared or answered, let us know. Drop your questions there. Every 2 weeks is fine. Tigran says, yeah. Yeah, this might be getting a direction. I mean, like I said, the goal of this workshop is also to get some tutorial material for the YouTube channel. So as long as we have some stuff, we might also record it just here live with some people joining.
To hire some contributors as well. Hopefully, after all these explanations, you should be more familiar and have more clues. And then at some point, we would like to have people contributing and extending the library, because it's really easy in the end to do it. So we want to educate in that direction.
All right. So then I guess that's it for today. See you all next time, or some of you. Let's see. Hope you enjoy Fuse in between. And yeah, keep your questions, suggestions posted in the channel. See you then.
Ciao.